This is part 4 of section 6.5, polar graphs. And in this section, what we're going to do is summarize our rose curves, and then we're going to look at a couple other common polar graphs that don't really have families, but are seen a lot. So, just looking back for a second, our rose curves, we had one where we had 4 petals, and we had all 3 of our symmetries. And then we had one that had 3 petals, and it just had the line pi over 2 symmetry. So how do we decide what orientation and how many petals do these curves have? So we're going to go through, and it is different slightly between cosine and sine. Cosine and sine gives us our orientation. So what we're going to see here, and I'm going to show you some graphs, is that with cosine, the equation looks like this. We have r equals a cosine n theta, where n is a positive integer. And n does a lot for our graph. So the domain for these, since we're relying on cosine, is going to be all real numbers, because cosine can take on any value of theta. And our range is going to be, now we have to take into account that a could be negative because we're not putting restrictions on it. So it's negative the absolute value of a to the absolute value of a. That's going to be our range. And you'll see that the A is how long the petals are. And then our symmetry for cosine looks like this. If n is an even number, we have polar axis, and we have theta equals pi over 2, and we also have pole symmetry. If n is odd, because we saw that with the sine, we are going to have just polar axis. That's for cosine. That doesn't look like an S at all, either time that I drew it. There we go. I don't know what's going on with my hand today. Okay, that's a little better. And then finally, how do we determine some of the characteristics of the graph, like the petals, things of that kind? Okay, so we have a max R, which is equal to the absolute value of A, and that's the length of the petal. And then how we determine how many petals we have. If n is odd, we have the number of petals. Let me use another color for that. Let's use this. So the number of petals is n. And if n is even, I don't know if you guys figured this out yet. Hopefully some of you did. The number of petals is 2n. So you have twice as many. And we can see that back in the 2 graphs. So for the 2 sine 3 theta, n was 3, it's odd, we had 1, 2, 3 petals. For the one before it, we had 2 sine 2 theta, n is 2, so it's an even number. We had 4 petals, or 2 times 2. So that's for cosine. Then for sine, our equation looks like this. R equals a sine n theta. And again, n is a positive integer. We're going to have the same domain and range. all real numbers because sine is also existing everywhere, and we have the same range. And then our symmetry is going to be slightly different. If we have, now we saw already that if n is even, we have all of the symmetries. We saw that in our first example. So we have polar axis, theta equals pi over 2, and pole symmetry. Now what is different is when n is odd, what we found in our example was that we had symmetry at theta equals pi over 2, because now the curve is oriented on the y-axis. Cosine ones are oriented on the x-axis. So if n is odd, your first petal will lay along the x-axis. If n is even, it'll be rotated so that you'll see that you have more than one petal. You have more than one symmetry. And then for odd symmetry for the side, we saw that it was laying along the y-axis. And if you change a to a negative, it flips it over. So that first petal that we saw here in this example would be flipped up to the top. This would be rotated, and these would be down here like that. And same with cosine. It lays along the x-axis, so it gets rotated when a is negative. So it's flipped over to the negative x-axis or negative polar axis. Okay, and then finally, this part is the same. So a max R of the absolute value of A. And again, that's the length of our petal. And if n is odd, this is the same. So what we have with odd, the number of petals is n. And if n is even, you double your n. So it's 2n. Okay, so there's two more curves that come up a lot that we want to look at. And I'm going to apologize in advance. This one is very hard to draw freehand. It's called the spiral of Archimedes. And what we're going to find is, and I'm just going to write it here, and you guys can verify it yourself, that our typical symmetry tests will fail. So you could pause the video and try them all if you're not convinced. And so I am just going to pick a series of angles here to show you the whole thing. So I'm going to do negative pi over 2, 0, pi over 2, pi, 3 pi, oops, I forgot the pi, 3 pi over 2, and then 2 pi. So I am going to start here. Wait, I guess it helps if I put the values in. So they're obviously just going to be themselves because it's just theta. By the way, in case you didn't realize, 1.57 is pi over 2. So they're just mirror opposites of each other. And they're just going to get bigger and bigger as we go. So it's going to look like this. Let me see if I can draw this. I'm just going to kind of freehand draw this. It's kind of hard. It looks like a spiral, like this. It'll just keep going, and I'll just stop there. And it's going in this direction. Now, if you were to make that negative theta, it would orient itself in the other direction. So that's the spiral of Archimedes. Let me do that in the calculator. It's a nice graph. So let me just add a graph page here. And let me just do that real quick. Oops, I forgot to say that I wanted a polar graph. It's going to be not a very nice looking. I'll probably get yelled at by the calculator because it won't recognize theta as a variable in rectangular coordinates. All right. So that's one spiral. That's just from 0 to 2 pi. So if we wanted to go on and let's see. Let's make this times 2. See if I can just squeeze that in there. 2 times 6.8. Let's go around again. I guess it didn't like that. Let me just double this. So that would be 12.56. Yeah, so we'll go around again. And you can see it just keeps spiraling out, and that's what it does. Okay, so that's one of our graphs that you sometimes see. Another very famous graph is called Lemniscate curve. And if you notice now, our R is squared. So just to go through the symmetry test real quick. And I guess it helps if we see the equation. There it is. Doing our polar axis. We're going to have, going to use the alternate one. Negative r squared equals 4 sine of 2 times pi minus theta. And so we get, simplifying this, we get r squared is going to end up equaling negative 4 sine 2 theta. So this is a no. And go through and do the work if you're not convinced. So if we do our line, we are going to get r squared is going to equal negative 4 sine 2 theta. So that's again a no. And then if we do our pole, we're going to get negative r squared equals 4 sine 2 theta. And that's going to be a yes, because when we square negative r, we get r. So it has symmetry at the pole. It does have one other symmetry, which is pi over 4, and you'll see when we draw that. And so if you notice, our table's a little smaller because we don't need quite as many values to graph this one. So we'll do 0 pi over 6, pi over 4, pi over 3, and pi over 2. And so we have 0, and here's why we only need these, is because we're going to have to take the square root of r squared. We're going to get 2 answers for each one. We're going to get plus or minus 1.9. We're going to get plus or minus 2. We get plus or minus 1.9 again. And we get 0. So when we put all these on here, we have 0 and a pi over 6, we're at 1.9 and negative 1.9. At pi over 4, which is in between these, we're going to be at 2 and negative 2. And then at pi over 3, we're back at 1.9 and negative 1.9. And then at pi over 2, we're at 0. So it looks like this. So we have 2 petals. That's the only way you can get 2 petals. Okay, so you can see that we do have symmetry along the line. Pi over 4. It's a different type of symmetry. And that's where we started this whole discussion of polar graphs, is the fact that these are sufficient but not necessary conditions for symmetry. If you remember, that was one of the first things we talked about, that these tests are sufficient but not necessary for symmetry. So here's a graph that has pole symmetry, but it does have another type of symmetry, pi over 4. So those are our polar graphs. We have our lumensons, we have our rose curves, and then we have a couple special ones. We have our spiral of Archimedes, and then our limit gauge. So we'll be doing a lot of work with these over the next few weeks. If you have any questions, please let me know.